So why I'm here is to compile Scala faster. So I went on Google and typed in Scala compiler is. And this is what comes out. And the second thing I want to talk about is the startup time of Scala compiler and other Scala programs. So before I start with the presentation, I would like to introduce what we do at Oracle Labs. It's a project called GraalVM. It's essentially a virtual machine built on top of the JVM. So it uses all of the runtime components from the JVM. But then it adds a JIT compiler and a truffle framework on top, which allow us to run multiple languages in GraalVM. So GraalVM supports at the moment Java, Scala, and all other JVM languages, and as well as Ruby, Python, JS, R, and all of the languages that compile to LLVM. GraalVM comes with additional tool that we'll talk about here, which is called Native Image. And this tool allows us to build native images from any Java program, including the GraalVM itself. So it allows us to run in the native code. So essentially, the slogan of the GraalVM is like run programs faster anywhere. So where do we run it? We can run in the OpenJDK, which is what we'll be presenting mostly today. Then we have a Node.js mode. We embed GraalVM into the Oracle database in a project called MLE, as well as MySQL. So today you can run JavaScript and Python in MySQL. And then finally you can run it standalone. So for more information, just go to graalvm.org and you'll figure out more. This is I can give 3 talks just about GraalVM. So because here we are talking about compiling Scala faster, I'll just show you a few of the things which the compiler in GraalVM does to make programs faster. So, sorry, before I do that. So the key features of Graal. Why is Graal better than other compilers on the JVM? So one of the main reasons, I think, is written in Java. And why is that important is because when you write your compiler in Java, you can easily refactor it, use all the tooling. It's much more modular, and in the long run, it pays off manifold. Then it has modular architecture, so it's very easy to configure, add your own phases, and change them. And it also separates the VM from the compiler by essentially snippets and provider interfaces. So this allows us essentially to kind of, because Graal came into the hotspot later, we had to kind of make an interface for every single thing we require from the VM. So the code is clearly separated. And then it's designed for speculative optimizations. That's what every JIT compiler does. And garbage collection, and it has aggressive optimizations. And out of these, I'll talk just about 2 of them, which I like. One is called partial escape analysis. So essentially, when you have objects in your methods, allocations, for example, this new car here, these allocations, if you do escape analysis, you're trying to figure out if you can remove this allocation and replace all of the usages just by the values that you have, which is in this case horsepower and name. And if you look at this method, here object car escapes in 2 places, here into add to cache and in the return car. However, this could be a very unlikely path, right? So what GraalVM tries to do is to have absolutely no allocations on the paths which are important on the hot path. So in this case, what will happen, so the car, essentially we will move the allocation of the car into the else branch, which is not a likely path, and then on the hot path, we will just have accesses to the fields. So this is something that is kind of unique to Graal, and which, especially in context of Scala, which has a lot of allocations, helps quite a bit and removes a bunch of them from the hot path. Another one which I really like is called simulation-based path duplication. This is essentially a generalization of an optimization which is called tail called duplication, because it works across every merge point. So if you look at this little code snippet here, where we have, we say if A greater than B, P equals A, and then else P equals 2, and when we divide the length of an array by P. So division, when you compile it down to assembly, is a very expensive operation. And if we have this being a slow path, and this being a fast path, which is executed most of the time, and we notice that in the fast path, P gets a type which is a constant type, always 2. We can, sorry. Oh. We can essentially do strength reduction, because we know that P is always 2. We know that x.length is greater than 2. So we can rewrite x.length divided by 2 with x.length shift by 1. And then, however, after the merge here, after the if, this x.length, this cannot be applied because it applies to the both of values. So what we do is essentially do a cost-benefit analysis, whether this is worth it. And this is how it looks. So we say benefit is a latency of a division minus the latency of the shift, and then times probability of the branch. And then we can compute the value, which is in this case quite high because the latency of div is very high. And then we say, because we duplicated code, you say how many instructions does this add on overall to the compilation. And in Graal, all of the nodes are annotated with an estimate how many instructions will they cause once the compilation is done. So we use that cost model to compute the number of instructions. And then we get this code in the end. Actually, there is a return, but in Scala, that's kind of hard to write. And then we get code that is 1 order of magnitude faster on the CPUs. There is a paper about this work, which you can look for more details. A key point is that essentially we move the code inside, but then we run additional phases that are kind of reducing the code size and doing the optimizations and then doing the cost. So we are doing a part of the compilation run in one of the phases to figure out how much do we save. And there is a few more of these which I don't have time to present. So it would be nice that my machine responds. Okay, so let's take a look at how Graal does on a simple program. So here I have a program which is doing a streaming operations in Java. So this is, you don't have to look at the beginning, but essentially we have a bunch of like what is equivalent of a case class in Scala. We have a person which has a sex, a gender, and so on. So it's a bunch of abstractions that you use. And then we have an array of persons of a certain size, and we will do streaming operations. So we do a filter, we select only male persons, then we do another filter with the height, we map the int age to int, and then filter age greater than 10, we do an average and do get this double. So, and if we take this code and run it on the regular JVM, we'll get something like this. So in the beginning we have some warm-up, and then we get around 180 milliseconds. Now if you run it with GraalVM, we get 4 times or 5 times faster code. So what GraalVM does here, is analyzes in depth where inlinings are relevant, and essentially does a few more tricks to convert all of this into a single while loop, right? So it kind of, this is an equivalent performance of a while loop. So, okay, nice, it's faster, so I think it's the recording app. Good. So then let's take it on the, the main problem, one of the main problems in the community is the performance of the Scala compiler. So what I did here is I took the Scala 2.12.6, and then I took the compiler suite benchmark from the Scala team, which is awesome, and it works really well. And then I took Graal and ran it. So Graal has two modes. There is GraalVM community edition, which is based on the core compiler, which is missing a few of the phases, and then there is enterprise edition, which has all of the phases, including the ones I showed included. And before I go on with the graphs, so in this presentation, all of the graphs are done in the same way. So on the left side, we have the speed up, and then on the bottom, we have the projects we run on the x-axis. All of the runs were done until complete warm-up. There is no turbo, and it was done in a proper benchmarking setup with no noise. So, and then we can see that these are the corpuses of code that we were using for compilation, and the Scala C with GraalVM runs essentially 1.47 times faster. Here 1.42 and 1.42, right? So and this is quite a bit for daily development if you save 1.5 on your compilation. This is an ideal world. All of the code and all of the output was essentially in memory, and there is no SBT. Then I added SBT, so I checked out a few projects which are kind of known in the community. So I took Shapeless, I took Scala C, and I took Akka. And then essentially this is what we get in real life. So if you take a project, what I did is I took SBT and enter the project, and then I say clean compile, clean compile, clean compile until it stabilizes, and then I compare the values for the last compilation. So, and for Shapeless, which is kind of shortly compiling, we get 1.26, for Scala C 135, and for Akka 135. And this is with all the noise, like all the updating and Scala reform stuff and so on. So this is what you essentially get if you take GraalVM. So essentially, how do we do that, right? It's very easy. So it comes in two versions. The community edition can be used freely by anyone, which gives around 10%, which we've seen in the previous slide. And essentially just download it, put it in your, run it on your laptop, in your CI, wherever you like, it's fine. And then for GraalVM Enterprise Edition, it's essentially a free evaluation license for non-production use, where for all the individuals, I would say compilation is a non-production use. So essentially just download it from here and get your compiler faster. Okay, so, and how do you do this? Well, it's very easy. You say just SBT Java home, and you give a path to GraalVM, okay? Or you can even put it into SBT opts. Yeah, so let's just do that. Just real quick to break the ice. It's a really stupid thing, but so here I have Shapeless. So we can do SBT. And there you go. So this is basically one download, and essentially one argument is dividing you, like it's getting you 30% of per compilation time. So and when you compile in SBT, you will notice that for small projects, the first compilation will be maybe 20% slower than the hotspot, but then already the second one will be faster, and all of the consecutive ones will be faster. If you take a big project like Akka, even the first one will be faster, because Akka compiles for long enough time for the VM to warm up, so it kind of evens out, so even the first one becomes faster. Yeah. So just take it for a spin. It hasn't failed a single time in all the benchmarks I've done, so I would consider it stable. And also, essentially, if you have any problems, of course, report, but also it's compilation, so it's not really important. Good. You will also notice that in the first compilation, your machine will use all the cores, but then later it basically stops. So. I
think you need a new laptop.
Yes, I do. This one is still from the lab. There we go. and so on. Every next time it's much faster. So let's not wait for my laptop. Good. So there you go. Just download it, take it out, compile faster, and write better code. So in the second part of the talk, I want to talk about the problem of startup in managed runtimes, especially in the JVM. So essentially, if you look at the JVM and when we look at the hello world, for example, in Scala, the time to just print hello world is like 100 milliseconds, which is in computer science eternity. And then if you look at the instructions, it's in like billions, and it takes a lot of memory. For JavaScript, this is running GraalJS on the JVM. It's 1.2 seconds to print hello world, which is an eternity of an eternity. So, and then when we look at the hello world in C, it takes 5 milliseconds, and that's mostly because of the OS stuff that's running, and it's just 100,000 instructions. So, and why is this? Because the JVM essentially does many things when it starts up, especially for the short programs. So first it needs to load all the classes, verify the bytecode. Then you need to either use bytecode interpretation in the case of the JVM or baseline compilation, which adds an additional layer and an additional overhead. And then finally you do just-in-time compilation, and because you're running a short program, you just compile your stuff when you finish the program. So you basically just wasted all your time on that. So, and in GraalVM we do the following. We wanted to get rid of this. Yeah. So we build this tool called Native Image. And what Native Image does, it takes any polyglot JVM program, so it can be written in Kotlin, it can be written in Scala, in Java. It takes all of that code. In case if you're building the image for Truffle and all the languages that you're running, like JavaScript takes that as well. It takes the VM which we've written, which is called Substrate VM, which is also in Java, and then it does points to analysis. Essentially, it finds all of the fields, all of the methods, and all of the classes that are reachable. So it cuts off most of the classes that you don't really need on your class path, and essentially uses Graal to ahead of time compile it into the machine code. So it can be compiled either into a shared library, if you have, we'll see this towards the end of the talk, or into an executable. And for now we support OS X and Linux, but in the end of the year we'll support Windows as well, and iOS soon. So essentially until probably very soon it will run on all the platforms. And then if you take a native image and then we take the same programs, what we get is well essentially hello world in Scala will be comparable to C. And hello world in JS, well, it's a bit slower, but still not eternity. So building a native image, it's kind of notoriously hard to do ahead of time compilation of languages like Java and Scala. So in order to get our native images fast, we introduced this mode of compilation called profile guided optimizations. So what we do is essentially, because the Graal compiler was originally built for the JVM, so all of the phases, all of the optimizations, they want to know which paths in the program are hot and which are cold. So you need to know all the probabilities for every branch you take. So what we do is essentially we build a native image in the instrumentation mode, where we instrument every conditional in the code and every method call, and then we get an instrumented binary. So this binary is a bit slower than the original one, but that's not important because it's anyhow running only before you ship your code. So then you can take relevant workloads, and then from those you build profile files, which you again feed into the native image. Just this time you say -pgo, and this in the end gives you an optimized binary that you can use later in production. So it's recording the show, that's important. Yeah. So let's take the streams that we had here. So it's already compiled, so we can just say to build the image, it's very easy. So this is native image which essentially comes with GraalVM. So you just say the name of the main class. And there we go. So these are the phases I explain. So this is the analysis, which kind of does the reachability. Then we basically compile, and then we just write the image. And now we can run test stream, but you will see that it's about 2x slower than what we had on hotspot. So what we can do now is do there we go. So this will add an additional phase to the compilation pipeline called instrument. You can see it here, which adds all the instrumentation. And then we can run that. It's even slower, some 10 to 50%, depends on the workload. And then if you can see, we will get this eprof. It's called default because we didn't specify, but you can also specify the file path, so you can kind of run multiple benchmarks and then just accumulate your profiles. And then if you do, there we go. This will now suck in the profiles, which we've seen on the diagram, and essentially compile the program faster. So native image is still not as sophisticated as the Graal in the original mode, because when you do JIT compilation, you can cut off branches that are never used, which you're never allowed to do in the ahead of time mode. So if you run this, we will not get as good performance, but we will basically, get better performance than what you get with GraalVM. So we got here about 30–40%. So yeah, so this is basically how PGO is used. So don't be afraid to use it. It's very simple. Just run one more build step before you ship the final binary. So good. And here is just for the This is how you use it if you have a dump file. So you can just dump multiple runs and then you basically specify them here. So let's see. Sorry, one more thing. So let's try this native image tool on. I have here this. I have made this script which is called Scala C image. Don't look at the length of the thing, but what it basically does is gives this class path to the Scala compiler. I took the latest version of 2.13. It says which methods have to be substituted because Scala compiler uses invoke dynamic in one place, so this needs to be substituted. But this can also be removed easily. And then it says which classes are reflectively loaded in the Scala compiler. So you need to kind of tell the tool which reflection, which dynamic loading is going to happen, and then we say give it the name Scala C. Okay. So let's build the native image of the Scala compiler. So this time we will not use PGO because it takes a ton of time. It takes a ton of time anyhow. So and then what I also done while this is building, I've written this script which essentially calls the Scala. This is equivalent of it's like a hacky equivalent of the Scala bash script, which runs Scala. So it passes the class path and all the stuff. What it needs in addition is the rt.jar, which you can see here. And the reason is that it's not present because this is a native image. So you need to pass it on a class path. So essentially, for now, I just built this image for the Scala C, the latest version. But with the next release, which is at the end of the month, I will make the versions for 2.12, and then hopefully we can add changes to Scala 2.13 so that we don't need these substitutions, this one substitution actually, so that you can build the image just with a simple command line. And also I'll publish the scripts, the link will be provided. So for the next, essentially from the next release, we'll be able to build a native image of the Scala compiler. 2.12 and 2.13. And if you think Scala is compiling slow, you should try native image. This is my daily life. almost there. Okay, and so while this is still compiling, what we will run here is this program which was written by my son. He's 6, so he started writing code, and it does some ASCII art. So we will use this here for the demo. It essentially, you will see what it does. Done. So don't complain about Scala compilation time. Okay, so this is the script I've written, and then we just, like any other Scala, we say, we can even time that. And you can say it's done in 180 milliseconds. And then let's run it. I have to use 213, otherwise it fails. And then we say, and then if we say this, which in Serbian means summer, it will print basically, I don't know where we put the for loop. It will print, the sunshine. And if it say winter, it will print snow, and the chimney has smoke. Okay, so then we built a native image of the benchmarking suite. So again, we have Scala P, we have vector, and RE2S. So, and this is a cold run. So we will run the benchmark suite essentially only for one iteration on hotspot and one iteration in the native image. And this is what we get. So for Scala P, you get like 6x faster because the first iteration just takes 10 seconds on hotspot. And for smaller projects, even more. So 13 and 9, which essentially, if you're working on a command line, is incredible. Right? Then we also compare the native image with the warm-up VM, and this is what we get. So on this graph, hotspot here is essentially a hotspot which doesn't use compressed pointers, and I put this, which is not a default mode on hotspot, and I put this intentionally because SVM at the moment doesn't support compressed pointers, and this makes a huge difference. And we are adding them in the next month or two. So basically, we will get this gap very soon. So, and then we take a native image, and then we take hotspot with compressed pointers and native image that we built from the Scala compiler that I just show you. And essentially the native image, the ahead of time compiled code, is comparable to hotspot. So here is 3% faster, somewhere is 2% slower, but in general, it's comparable. And once we get the compressed pointers, this gap from here will go here, basically. So, so I find this quite amazing that an AOT image is faster than the kind of the fastest compiler on the JVM at the moment. So, of course, because you build ahead of time, there are some restrictions. Essentially, all of the whole image is built on the closed world assumption. So all of the dynamically loaded classes must be known during the image build. In some cases, invoke dynamic, which generates new code or just switches the code, like in the Scala compiler, will not work. And you cannot do things like bytecode generation at runtime. So you can generate any bytecode during the image build time, but not at runtime. So if something happens in the static fields or in the initializers, that's fine, but later in the runtime, it's not allowed. And then we have quite good support for the JDK. Some of the things that we don't care about are still missing, but the community is starting to evolve, and we are faster and faster fixing them. For example, swing and AWT are still not implemented. And this is unfortunate for the Scala compilation, because macros are dynamically loaded and they're basically distributed all over Maven. So it's very hard to kind of build a native image which would work in an SBT setting, right? Because you would need to know either build. Essentially, we have a few possible solutions, right? So you can build a custom image for your project with your macros, and then your developers can use it. But that's kind of I don't know. It would require quite some SBT hacking, and I don't know if it would be feasible. In the midterm, we will definitely support some kind of dynamic loading, so your macros could be compiled separately with a native image. And in the long term, we will definitely support dynamic class loading, but this is a longer period. So in the end, we will have Scala C, which essentially runs fast right from the start, and it runs faster than a hotspot, and it will be probably licensed as free to use because it's a native image. It's not GraalVM itself. So, but if anyone is interested in one of these projects, kind of, send me an email. We can work on it. I didn't have time. Yeah. So, and then in the last part of the talk, I will talk about the shared library part of the native image and interop with C. So essentially, what we support in Java are annotations to kind of hook into the native libraries. So we have a bunch of here is just for an example. I won't go into all of them, but you can essentially call C functions. This is very similar to Scala Native. So you can define constants, you can define structs, pointers. You can have a context for compilation, which libraries you're using. And for example, this is our implementation of nanotime in SVM. So we write the whole VM is written basically in Java, but if you look at it, it's essentially you say stack value.get. So this is essentially a stack allocation from C, and then you call C functions and compute it. All right. So, and why am I mentioning this? Because in the Scala community, there's this project called Scala Native, which kind of does the same thing. It does one thing very well, and it has essentially an interface which is idiomatic to Scala, and it's very intuitive to use. And essentially, Scala Native can also be implemented by GraalVM. So if you take the native image, and we take the Scala Native intrinsics that we have, and then we just compile them into the primitives that we have here, which is not always easy, but way easier than implementing Scala Native. We can get the same thing basically. So, and it can be also implemented probably just by a simple compiler plugin. I wouldn't think it's more than a month or two of work to do that. And then what you get with this is that you get all of the Jvm libraries. So are they from Kotlin or Clojure or Scala itself for free. And you don't need to rewrite the whole Jvm ecosystem, which is kind of a big thing. And so what I did is I took the Scala Native as a benchmarking suite. So I took the benchmarks from there. So orange is the native image, just the vanilla one without PGO. And the red one is with PGO. And so this is Scala Native without their version of the PGO because it's not published yet. And it's using this Imix GC, which is supposedly the fastest GC for Scala Native. So, and if you look what native image does, essentially it outperforms it even in the open version by 2 to 5x and then up to 10x with PGO. So, yeah. So in summary, we get with GraalVM, we get Scala compilation faster from 1.3 to 1.5x, and I personally believe we can even go better. And then we can get native images of Scala programs, fast startup and low footprint. We've seen about 10x faster at startup. It's also faster than the hotspot JIT compiled code. And essentially, if you have a cool tool that you like and it's in open source, for example, Scala Reform or Scala FMT, just contact us, and I think we can get the free license basically for the PGO and all of the enterprise features. So you will get essentially the fast startup and faster peak performance, which is kind of nice. And then we have open problems, which are effective support for Scala macros in the native image. So I'm open to discussion. I think this needs to be solved. And then we need support for the Scala Native interoperability with C. So we can run Scala Native, but we cannot do C interop because Scala Native uses their own intrinsics. And I hope that in a year or so, when I go to Google, we'll get something like this. So Thank you very much. All of the demos, yeah. So all of the demos will be published here. I work for Oracle, so it takes an approval or something, so whatever. But really the next release at the end of the month, we'll have it all there. Yeah.
Okay, thank you very much. And I think I open the room for questions right away.
First come, first serve.
So what does EE do that CE doesn't do?
The things I've shown, well, you've seen one of the optimizations, and as we
Partial escape analysis?
partial escape analysis is in both. But the path duplication, for example, is there. Inlining is better, and a few other small things. But I think, yeah, these are the key things.
So I'm curious. I didn't get quite where GraalVM operates. It operates on bytecode, right? So does it also need the source code?
No, so it doesn't need. It operates all is on bytecode. So that's our input. So it's basically, if it works in the OpenJDK, it essentially is just like normal hotspot when you run it. So it parses bytecode and gets the assembly out. Native image also operates on just pure bytecode. So it just does it ahead of time. So
yes, all the optimizations you have shown, they don't actually operate on the source, but they operate on what happens on bytecode level.
No.
Are there any changes related to inlining of megamorphic call sites?
Oh yes, but you've seen the streams thing. I didn't do the Scala collections in the interest of time, but it basically it's pretty much the same results. You get for these like small snippets of like collections, you get 2 to 7, 8x depends, right? So yes, it does help.
Can you tell a bit more what exactly you do? What exactly changed in megamorphic call size?
Well, because you inline more, right? So when you inline more, you typically when you inline more, you get when you inline more, you get essentially less megamorphic sites, right? So the problem is, in some cases it will still happen, right? But the more you inline, the more code you have, and the less megamorphic your calls are, right? So that's kind of the simplest answer I can give you. Yeah.
What does the rest of the tooling look like? Can you still make thread dumps, heap dumps, profiling, that sort of thing?
Yeah, all a good question. Thank you. I didn't put that to not to complicate. Yeah, so you can use GDB to debug. So when you debug Java, it works pretty well. When you debug Scala, well, it kind of gets to you all the low-level stuff. So it kind of, you can get to your stuff, but it takes a bit of effort. I guess we would need someone to do that. Well, if people start using it seriously, we would probably do that, right? Because we have this, for GDB, we have this kind of Python helpers which allow you to interpret the language-specific stuff, because there is like a mismatch between what you get from what you get from debug info in the image, right? So, and then heap dumps, yeah, that's supported. Profiling is supported. Code coverage will come soon, because this PGO feature also kind of, it also tells you which branches were executed. So yeah, so maybe it's not as, so the native image part is not as good as the hotspot. I would still prefer working on JVM, and the image build times are quite long. The Java part is equivalent basically. So you have all of the stuff the same. Yeah.
As far as sorry.
Yes.
As far as I know, only Java 8 is supported right now. Is that true? And if so, are there Java 9, 10,
Java
11?
Yeah. So this what I presented is Java 8. We ship a modified version of Java 8, which allows us to put Graal inside. With Java 9, the JVM CI, which is essentially the compiler interface, comes with the VM. So yes, this will be running on your regular Java. You can just add a bit of a class path for your Graal compiler jars, and that's it.
So I will be able to use the Java 9 runtime jars.
Yes.
Okay.
Yes. You can use them even now, but I think we don't still ship with Java 9, but internally we do tests on them and it all works. Yeah.
Thank you. We see a good performance improvement for the GVM-based languages, but what about, and seems like it using the bytecode as a source and uses a static analysis ahead of time compilation. But what about the dynamic languages such as Node.js, Ruby? What is about performance there?
Good question. So JavaScript is the same as V8 if you don't take regular expressions into account, which we're working on now. It's even about 1% faster on like a geo mean of all the benchmarks. Ruby and other languages, because V8 has a big team working behind it, right? So it's super optimized. So other languages are way faster. So Ruby is 4x faster than the JRuby implementation, and R is like 5x, I think, and then Python is also way faster. So basically, LLVM is a bit slower than when you compile it with the LLVM compiler, which is unfortunate. I believe we can be faster there as well. But basically, it's faster, it's slower at warm-up. We haven't worked on warm-up, so V8 has a super good interpreter, and the compiler is tuned for starting up like fast. In our case, you can use it in a shell scripting mode. You get pissed. I get pissed when you use it. So basically, only in the server mode at the moment. Yes.
Okay, in Java 9, is the compiler interface implemented with Enterprise Edition or Community Edition?
Well, it's the licensing thing, right? So essentially, the compiler interface is the interface, and then you can put, whichever edition you want, right? So for non-production use, like compilation, for example, you can put the Enterprise Edition, and otherwise you can just take the Community Edition, which also gives speedups for Scala. Right. And it's also already used in Twitter. They use it in production. So there is a great talk by Chris Tellinger. It will be in the Scala Days New York. You can take a look at that and his experiences from there. Yeah.
A lot of the time people put resources on the class path, and I try to use resources on the class path with native image, but that can't work because class loader is not supported. Will there be a time frame to support that use case?
No, it actually, as long as you know stuff ahead of time, it all works. So at the moment we have resources supported, as long as you know them while you build your image. You cannot do it later, but yeah, we will probably support this in. But this is not kind of a near future thing because we have bigger fish to fry at the moment. But it seems to be. I mean, yes, in the end we will support it, but not at the moment.
So, any more questions? Okay, there's one. I'm standing right at the...
Does Graal create a lot more assembly code than C2? And is that a problem?
It does create more code. I haven't seen that it's a problem. I think this paranoia about generating assembly code is... it's a bit old school. I think it's not. I mean, on laptops it works. On server machines, I haven't experienced any issues. So, and we are also not. We are not in the mode where you generate recklessly assembly just to get every bit of performance. So we are quite conservative. Both the inlining and the path duplication. Essentially, all duplication phases are very conservative about that. So yes, it generates more, but not with like orders of magnitude. And also interesting, what I found interesting is also I was playing with the parameter tuning for the Scala compiler, and then I was even generating like 2 times more code and 3 times more code, and the performance went up only by 3%. Right? So it's kind of I think the inliner is doing a very good job in finding what really needs to be inlined. Right? And another thing I find interesting is that, for example, this path duplication, although it should always duplicate code, in some benchmarks it even like reduces the code size by far. So yeah.
Okay, thank you very much. I think
there's
one more question. Okay. You're the bad guy keeping people away from the beer.
Yeah.
So I have a question about your benchmark results against Scala Native. So you said that in some cases you go to up almost 10x compared to Scala Native. And from Dennis' measurements and benchmarks, he says it's 2 times slower than Hotspot. So that would mean that you're around 4 to 5 times faster than Hotspot. Is that correct?
That's not. Maybe I can rerun the benchmarks, but what I did is how I ran them is I took the SBT and I took the machine that I do the benchmarking on, so everything the same. I said I did SBT benchmarks /run, and then for ourselves I did a native image basically of the main class of the benchmarks and do run, and then I took the values out, and yeah, that's it.
Okay.
So but I will rerun that, yeah.
Okay.
And update the slides if it's not correct.
Thanks.
Yes.
Okay, thank you very much, Vojin.
Yes, thank you.
And thank you very much, everyone.